Hey everybody, welcome back. It's Mr. Rhodey with the reminder to wash your hands, but also excited about starting this new unit on trigonometry with you. I know this is coming off of the announcement that we won't be seeing each other again this particular school year, but hopefully we'll have a chance to catch up face to face either through Zoom help sessions the next 6 weeks or definitely next year when we come back in the fall. But don't forget to download the new book PDF for Unit 6. We're going to pick it up and do Activity 31. So I'm going to hopefully split this into two separate videos to make it a little bit easier for you to watch. But I wanted to follow up with some of the notes and questions you guys had from the video from James Tanton last week. I hope you enjoyed that. Obviously, the vocab and some of the trig we found was accidental or came from different misinterpretations of other languages. So it's kind of just neat seeing the human side of things, how math is just constructed by human beings with all of our flaws, and we just try to keep getting better each and every time we do something. The approximating where an angle lands. So hopefully through this week, you'll get better at drawing the angles. And again, it's all approximating and kind of getting a sense of where things land on a circle. So we'll keep a lot of drawings going on. Why is tangent called tangent? So we might tackle that on Thursday when we actually introduce the tangent idea back in. Is there a formula? Do we draw it every time? So there are formulas we're going to introduce this week, but really I wind up drawing it, 9 times out of 10 or after using it so many times it becomes memorized. So drawing is going to help you know whether the values are positive, negative, what quadrant it is in. So drawing is your most important piece. How different is this than the trig and geometry? So we're not just going to be solving triangles. We're actually going to be graphing these things on the XY plane. And so you're going to get these periodic functions that look like waves, which is going to have then applications to how weather changes, radio waves, television waves, all that kind of good stuff. And then we'll use a calculator. For graphing, we'll start to explore some stuff, but a lot of this is going to be non-calculator because you're just getting a sense of the basics and building it from scratch. So um, I'm excited to walk through this with you. Again, this first Tuesday is mostly focused on angles and radians and this interactive Desmos activity that we'll have. So hopefully you've got the PDF ready. You can follow along and take notes, and then there'll be points in the video where I'll ask you to pause to try some stuff on your own. Okay, first, if you're thinking about where are we heading with this? So again, this is Unit 6 as we're looking at it. So all of this is focusing on trigonometry. So where are we heading with it first? Well, this week, or actually just today, we're going to try and understand what radian measure is. We're going to try and calculate arc lengths, which you've done in geometry, and we're going to convert between angles and degrees, and this new thing called radians we're going to introduce today. Okay, so we're starting off on page 477 of the Unit 6 notes on trigonometry. And as you can see, we're going to develop formulas for the length of an arc and describe radian measures. So let's start with that. Over here on the right, you'll notice I've said, what is a radian? The radian is a length of the radius along the outside of the circle. All right, and so we're going to describe that with pictures here and investigate that through arc lengths as we go. So let's start with our situation. You can read through this great paragraph about the architecture firm and the circular restaurant rotating around at the top of a building. Pretty cool tourist attraction. And so they ask us to say, how far from the center is a customer seated at the window? Well, we know the radius is 50 feet, so it's going to be 50 feet. So how far from the center? 50 feet. We can kind of draw a quick picture of that. So there's 50 feet. And then we're going to find the circumference of a circle with this distance as the radius. So the circumference, again, is going to be this distance all the way around the circle. And let me go ahead and calculate that. We've got the formula over here from last year. So the circumference is equal to 2 times pi times a radius of 50 feet. So my circumference is 100 pi feet. We're leaving it in terms of pi here. So that's about 314 feet if you were to use a calculator. So how far along? What portion of the circumference now is generated by a 60-degree rotation? So if I draw us in 60 degrees, now I'm looking at just this blue portion, right? How much of that? Well, it's 60 out of the total of how many degrees? 360. So it's 60 out of 360 times that 100 pi feet. And again, if you're using a calculator, if we left it in with pi, that would give us 6,000 over 360 pi feet. And again, we could start to look at this, but really it's 1/6 of it. So 60 out of 360 is 1/6. So times 100, that's 100 over 6, or 50 thirds. So 50 thirds pi feet. If you wanted to get an actual number for that, again, 314 divided by 6 would give you an approximate decimal answer. So that's on the outside. The key is we're interested in what's going to happen with people that are not at the window, but what about people that are at 10, 20, 30, 40, or 50 feet? They're going to travel different amounts depending on where they're seated. This is kind of a cool thing. It's true for record players, CD players, but it's kind of neat here. So we're going to make a table of this and calculate all those different distances. Notice it's probably getting smaller as you get close to the center of the circle with how far they're going to travel. So go ahead and pause and go to the next page. So like I said, we're going to fill out this table to figure out the circumference for each of these different sized circles for if I'm at 50 feet from the center, 40, 30, 20, 10, 1, etc. And then I'm going to have to multiply by 60 out of 360, or 1/6 of that, and get that distance. So we've already done that first one. So if you want to recalculate it from the front page and then try it with 40 feet, 30, 20, 10, and 1, pause the video right now, and then the answers will pop up shortly. Okay, so here are the answers popping up on your screen. You can check your work. Again, the circumference, 2 pi times whatever the radius is, and then how much is being traveled during each of these 60-degree rotations. It changes depending on how far away you are. It winds up being multiplied by 60 over 360, or 1/6 is that fraction. And so you notice you're getting a lot of the same patterns here. So this pattern is, what I wind up with is actually the radius of 20, if I'm looking here, times pi over 3, radius of 10 times pi over 3, the radius of 30 times pi over 3, radius of 40 times pi over 3. So this pi over 3 seems to be an interesting value here. And so this is going to start walking us towards this idea of what it means to be a radian, because we're going pi over 3 radians around my circle. If I took that much, right, on the outside of my circle, this is what we're going to call pi over 3 radians. And it doesn't matter if it's a 50 foot, 40 foot, 30 foot, 10 foot. They're all the same radians because it's all the same angle of 60 degrees. But in terms of feet, it's different amounts of feet for how much it's actually traveling. So let's look at this in this idea of arc length. So how big is this arc length that we just calculated every single time for this 60-degree angle? Well, if you remember, arc length, which we're going to call S, back in geometry, was actually what we call the percentage of the circumference. And what was the circumference? The circumference was 2 pi r, and this percentage was the angle divided by 360. So in our case, since we're looking right now just at 60s, we're going to change it in the future. But if I'm looking just at this, 60 out of 360 times 2 pi r, or 1/6 2 pi r, or pi over 3 times r. That's the formula for arc length of any 60-degree angle. So what we're eventually going to do is replace this idea of 60 degrees. This idea of 60 degrees is also known as pi over 3 radians as well, because that's going to be this same number for all of the 60-degree angles, regardless of the size of the circle. Go ahead and turn to the next page, and we'll try going from there. So next up, page 479. Okay, we're on the next page, and so we can use this arc length formula to find how far anybody travels for any radius at any angle. So we have at this diner seated 25 feet, so that's my radius, and then now if it's going 120 degrees, I can go and just fill that in. So I get 120 out of 360, which will actually be 1/3, times 2 times pi times 25. So that winds up being 1/3 times 50 pi, or 50 pi over 3 feet. And again, we're not going to use calculators here. You could approximate that. It's going to be around 52-ish feet with a decimal if you use your calculator, but right now we're kind of going through it. So you're going to go ahead and do this same formula, angle out of 360, except now the angle is only going to be 90 degrees for all these different radiuses. Practice with that formula, and then check your answers here in one moment. Go ahead and pause and try it yourself. So you've used these arc length formulas before. Angle over 360 times 2 pi r, which is our circumference. But we're trying to simplify it and see some patterns here. So I went ahead and said, okay, well, if I have 90 over 360 here, that's going to be 1/4. Quarter times 2 is a half. So really I have pi over 2 times the radius. So that's pretty nice. If I compare that, remember this is for a 90-degree angle. If we compare that to the 60-degree angle we had before, s equals pi over 3 times r, we realize, okay, 60 degrees goes with pi over 3, 90 degrees goes with pi over 2. This is interesting. There may be this conversion for all of our angles. So now 12 asks us, hey, what about the one where we did 120? What's the number there? Well, here's what I'm just going to do. I'm going to use logic. If 60 is pi over 3, and if I double 60, 2 times 60 equals 120, 2 times pi over 3 must be 2 pi over 3. So 2 pi over 3 must be the constant that goes with this idea of a radian for 120 degrees. So really interesting here. We're going to start doing this on the next page, and then the second video will dive even more so into radians. Okay, here we are on page 480. We're going to be looking at this circle, which looks like what we saw from James Tanton in last week's video. This constant proportionality for arc length, we're going to reduce it down and just look at a unit circle, something with a radius of 1. So then the radius really doesn't matter. We're just going to have that constant pi number involved here. And so when we think about this, what does it mean as I go all the way around this? Well, my circumference, remember, is going to be 2 times pi times the radius, but my radius here is 1. So my circumference is 2 pi. So if I travel all the way around this circle, it's 2 pi. On the flip side, if I change to red here, when we're looking for a formula in terms of arc length for just 180 degrees, so that's starting here and going all the way around here, that's half the circumference. Well, what's half of pi? What's half of 2 pi? Well, then 180 degrees must be pi in terms of what we're looking at. So that's pi in terms of length. It's our pi in terms of our radius. So pi radians, so 3.14. If I laid out 3.14 of my radius lengths out here, it would take me all the way around. 3.14 of those, it would take me all the way around that half circle. So pi gets me halfway around the circle, 2 pi gets me all the way around the circle. And so now we introduce this idea of the concept of radians. Okay, one radian is the length of one radius. So pi radians is about 3.14 radiuses or radii. And so laying those out in a curved fashion would get me halfway around the circle. Okay, so we can use this relationship to go with there. So now that we know radians with degrees, we can do some nice proportionality here. So I know for conversion, I know that pi radians goes with 180 degrees. So pi with 180. What does that mean about 30 degrees? Well, x is my unknown. 30 is my degree. So radians on top, degrees on the bottom. Cross multiply, I get 30 pi equals 180 times x. Divide both sides by 180. And I get 30 pi over 180 equals x. 3 over 18 is 1/6. I get pi over 6. So pi over 6 radians is the same as 30 degrees. And you're going to practice converting a lot of different values from degrees to radians here. So let's go and do 45 in the same way. Pi over 180 equals x over 45. Cross multiply. 45 pi equals 180x. 45 pi over 180 equals x. That will actually reduce to pi over 4 equaling x. So pi over 4 radians is the same as 45 degrees. 360, you could do the proportion as well, but I know 180 goes with pi, so if I double 180, I'm going to double my pi's, so 2 pi. 2 pi radians or 360. And so again, you can even just use that logic of proportionality to have with you. So what I'd recommend is, now that you've seen that, you practice 15, 16, and 17 on your own. Then I'll show you the pictures. We'll write down a couple of things on our word wall to help, and then we'll pick up the second video and go further in this idea of radians. Okay, here are those answers for 15 through 17. You can pause to check your work. And then from there, remember, you want to start to kind of develop things. So what I love about this is you could do the proportions here, but this 135 is just 45, 45, 45. That's three 140. It's three 45-degree angles, so 3 pi over 4s, if I'm thinking about it that way. So as I think about that, that's 3 pi over 4s. 120, as we saw, was 2 pi over 3s. Pi over 3 was 60 degrees. 3 pi over 2. Pi over 2 is 90 degrees from what we saw before. And so 3 90s is 270. So 3 pi's over 2's is also this. So you'll get used to just recognizing that instead of always having to do the conversions. So again, in summary, if you want to download the word wall, the big things from our first video today are the formula for arc length, which should be pretty basic. The idea of what a radian is. It's the length of the radius around the outside of the circle. And we built that from this idea of arc length with a radius of 1. And so we saw this constant that 180 degrees was the same as pi radians, because half a circle is 1 pi, while a full circle is 2 pi. And we can convert any degree measure to radians using this proportion at the bottom here. Vice versa, if they gave us a radian measure like pi over 2, we could also cross multiply and solve for it in degrees, which we'll do in our second video, and come up with a few other formulas. Because really this thing up here, this angle over 360 times 2 pi, if you drop the r, that'll also convert to radians from degrees. So there's a couple of different ways to do that, and we'll pick that up in video 2.